Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, I'm going to go into using the midpoint rule and the trapezoidal rule to help find the area under a curve, or basically to integrate numerically. This is a pretty easy process if you have a small number of subintervals, but as you can see right here, I'm dealing with a problem that has 100 subintervals. So we have some function. In this case, our function is the sine of the cube root of 1 minus x squared times e to the negative x. And we're dicing that into 100 subintervals and then using the midpoint and trapezoidal methods to go ahead and find or approximate the area underneath the curve from -2 to 7. Now, as a reminder, both of these methods are going to require us to know what our average width is, and therefore we need to know delta x. This formula right here is going to be very powerful whenever you're going to integrate numerically. All the methods that we use, at least at the undergraduate level, well, maybe even the lower division level, they're going to have delta x's that are constant. Now, I'm letting you know that if you go into actual numerical integration, like in upper division and graduate level work, your delta x's are actually going to vary, just depending upon how quickly the function is changing over a given interval. But for right now, let's just pretend as though our delta x is not changing. In this case, a is equal to -2 and b is equal to +7. So let's go ahead and plug those into our formula, along with the fact that n is equal to 100. Now you may think that that looks pretty terrible, 9/100ths, but the reality is you're not doing this work by hand. All the setup here you are doing by hand, but once you're done with the setup, you're going to run over to a calculator, or better yet, something like Desmos, or something like Excel or Google Sheets. We will also need to know what x sub I is. Again, this definition does not change throughout all of calculus. This still remains the same. We define x sub I to equal a plus I delta x. In this case, again, a is -2 plus I times delta x, which is 9/100. And that is our setup. That's all we really need to do, other than recalling what the formula structures are for the midpoint and trapezoid methods. For the midpoint method, we have that m sub n, in other words, midpoint method with n subintervals, is just the sum, the Riemann sum, of heights times widths. Remember, the function value here is the height of the rectangle, and delta x is the width of that rectangle. Notice in the midpoint method that we're evaluating the function at the average of the endpoints of the ith interval. Our ith interval goes from x sub I minus 1 to x sub I. We have some function above or below. Just to make it kind of interesting, I'll put it below. And to create a rectangle here, we're going to go ahead and take the average x value for that interval, and that corresponding function value will give us what we will consider to be the height, quote unquote, of the rectangle over that interval. That's what the midpoint method does. It just takes the midpoint between x sub I minus 1 and x sub I, or in other words, the average x value, and evaluates the function there. Now on to the trapezoid rule, which there's a nice closed formula for, but I think it's a little bit better to see the trapezoid rule mechanically first. So let's zoom in here. The trapezoid rule looks very similar to the midpoint rule, but instead of averaging an x value and plugging that into your function, you're actually averaging the outputs, the function values. You're taking the function value at the left endpoint of your interval and the function value at the right endpoint of your interval, and you're finding the average of those two y values. Visually, what this is doing is it's saying, well, what's the average between this y value right here and this y value right there? Now, because my function I drew here is not erratic enough, it's not really much of a difference between those two y values. However, if I change my function to look kind of like that, then you could sort of visualize the trapezoid rule as saying, well, I happen to know this y value here. I happen to know that y value right there. The average height is probably somewhere around here. And so we're going to go ahead and say, well, this is the average height. And so therefore we'll build a rectangle based upon that average height, and we'll find the area of that rectangle. However, mechanically, really what's going on behind the scenes, if you've ever recalled, or if you can recall, way back from your pre-algebra days, the area of a trapezoid is actually the same exact formula. It's the average of the y values times the width. That's the area of a trapezoid. And so therefore this formula for the trapezoid rule, and that's why we call it the trapezoid rule, is actually giving us the area of a trapezoid. Kind of a neat way to do it. In both cases with midpoint and trapezoid rule, you're just finding averages. Just one happens to be of x values, the other happens to be of y values. And if you've played with the trapezoid rule long enough, you happen to know that the formula condenses down somewhat nicely to be delta x over 2. As you can see, every term is going to have a delta x over 2, so we can factor that out. And then it will have this pattern to it: f of x naught plus 2 f of x1 plus 2 f of x2. And that plus 2 goes on and on and on until you get to the n minus first value of the function, and then you only have one of the x values, or the function values at x sub n. And that is mainly because of the fact that when you're using the trapezoid rule and you have, let's just say, a bunch of slices in here, each of these slices has a trapezoidal top on it, or a cap that connects the y values at their edges, which looks kind of nice actually, to be honest with you. And if you zoom into any of them other than the edges, if you zoom into any of these trapezoids, you'll see that, for example, in this trapezoid right here, it's using this y value and that y value to compute the area underneath that trapezoid. You're just averaging those y values and multiplying it by the width of that slice. But if I move over to the right one step here, the next trapezoid ends up using that same exact y value and the next y value on its right hand side. And if I move over to the right, the next trapezoid again is using that same y value of the previous trapezoid and the y value to the right of this trapezoid. So every single y value gets used twice, with the exception of the first and last trapezoids. This first trapezoid right here, it obviously will use its leftmost y value and its rightmost y value. However, when you go to the right here, this guy is not going to hop over here and use this left y value. No, it's going to use this one right here and this one right here. So this lowly little y value at the end kind of gets ignored. It only gets used once. And that same thing happens over on the far right. When you find the area here of this trapezoid, you do use the y value on the right and the y value on the left. However, the previous trapezoid, it also used the y value on the right, so that gets doubled up and used twice, and on the left. But the one here, well, that little guy only gets used once, and that is why when you look at the closed form, the left and right edges have unit coefficients, because they only get used once. Anyhow, let's go ahead and see how you can use technology to help you compute the midpoint rule and the trapezoidal rule with 100 slices, or how many ever slices you want to use. Actually, before we hop over to Desmos, because I was about to go over there and I realized it might be nice to have a conversation here. When you go over to Desmos, first of all, you're going to have to type in the function name. So we're going to let f of x equal the function we're trying to integrate, which is sine of the cubed root of 1 minus x squared, then times an e to the negative x. So that's what we're going to type in as our function. However, when I go to Desmos and I type in a summation, and our summation is going to go from 1 to 100, because that's what we need to evaluate it over, Desmos is not going to understand x sub I minus 1 and x sub I. So we're going to have to write in what that means, because it has no definition for what x sub I is and what x sub I minus 1 is. So we're going to go ahead and right now just rope up what x sub I is, and I'm going to go ahead and write down what x sub I minus 1 is. So now if we type those directly into Desmos, it will actually understand that. However, I still want to clean this up a little bit. If you're going to go into computer science, if you're going to do any type of coding, you really want to pre-compute as much as possible, especially when you are going to code something for a big project, because any way you can save computational power, you want to. So if you can pre-compute some things, you should. Remember, we're trying to figure out what that highlighted stuff is right there. So let's go ahead and figure out what x sub I minus 1 plus x sub I all divided by 2 becomes. Well, x sub I minus 1 is a negative 2 plus the quantity I minus 1 times 9/100ths. And then we're going to add to that x sub I. X sub I is the same negative 2 plus I times delta x, which is 9/100. Forgive my plus minus there. Let me go ahead and fix that. And this is all going to be over 2. We can actually help the computer by pre-computing a little bit more. And we get down to this point, even this, however, we can help the computer with. I'm going to go ahead and divide that 2 into both of those terms in the numerator. So we get a negative 2 plus 9/200 times the quantity 2i minus 1. Even that can actually be simplified a little bit further. And that can further be simplified to this number right here. And we can do one more step. That'll be negative 409/200 plus 0.09i. Just as a warning here, I is not the imaginary number. It's just an index. You could actually rewrite that first fraction as a decimal if you so choose. There's nothing wrong with that. You're just helping the computer out a little bit. That's all. So now we know that when we write this into our Desmos code, we can go ahead and write it this way. It's the summation. Let me zoom in for this. And we're going to go from I equals 1 to 100 of f evaluated at, and then I'll just steal that information over there, negative 2.045 plus, I think it's a plus, yeah, 0.09i. And remember, this is times a delta x, but that can be held off until the very end. So I'm going to go ahead and just write that over here. The delta x is 0.09 or 0.09. Trust me when I say pre-computing does speed things up. With today's computational efficiency that we have and the fact that we have very powerful machines, you probably wouldn't notice very much. But I'm telling you, I've worked on projects where you do a bunch of coding and then hit enter and come back a month later for the results. So it is very important when you can cut corners or help a computer out that you do that. Rather than showcasing the trapezoid simplification right now, let's go ahead and just focus on the midpoint rule here. So here we are in Desmos. Notice that I have actually already written the function f of x is equal to the sign of the quantity 1 minus x squared to the 1/3 n quantity, and that is being multiplied by e to the negative x. That's our function that we were concerned with. And now I'll go ahead and just hit enter and say that m is equal to, and I'll type the word sum in, S-U-M. Notice the index on this is preset to be n. You could change that if you want or keep it. I'm going to change it to be an I just to match my notation, and I'm going to go from I equals 1 to 100. Now remember as well, we were going to multiply the front end of this by the delta x. So there's delta x right there, and then our function. And our function, remember, it's going to be a negative 2.045 plus a 0.09 times that index I. And when you do that, you get a pretty decent approximation for the area underneath the curve. Again, this was from negative 2 to positive 7. That's why our delta x is 9/100. It's because b minus a ends up being a 9. So that's actually not too bad. It's much faster using Desmos than it would be if you were to use something like, let's say, Excel or something like that. Since you have Desmos at your fingertips, you might as well use it. Now, hopping back to the actual whiteboard here and talking about doing the trapezoid method or trapezoidal rule, whatever people want to call it, you can call it whatever you want. using a trapezoid rule with this is not as difficult, actually, because we're not adding those x values. So when I go over to Desmos, I am literally going to enter in the 0.09, let me just write it this way, times the summation I equals 1 to 100, and then it's going to be the function value at I minus x sub I minus 1 plus the function value at x sub I, all divided by 2, and then we already moved the delta x out front. A little arithmetic, again, can go a long way for your computer. This is just a 0.09 times the summation I equals 1 to 100. And now I'll go ahead and let's see, do some simple arithmetic. And this will compress down a little bit further. And this is what we're going to plug into Desmos right here, just like this. No need to get any fancier than that. That's as good as it can get. So over in Desmos, I just type in t is equal to, we have that 0.09 hanging out, and then we're going to multiply it by the sum. So I'll just say times, I probably don't need that times. I'll just type in sum. And again, I'm changing the index to an I, going from 1 to 100. Start a fraction, make sure that denominator is a 2. And in the numerator, we have the following. A negative 2.09 plus 0.09i, that's inside of f. And then we're going to add to that f of negative 2 plus 0.09i. Notice the trapezoidal rule has a slight discrepancy from the midpoint rule. Well, it's just they're two different rules. In fact, you probably already know this because of lectures in your course, but maybe not. The midpoint rule is twice as good as the trapezoidal rule. In fact, that often throws people off because visually the trapezoidal rule looks better, but it's not. That's an illusion. The midpoint rule is actually a better rule to use. Computationally, it can take a little bit more effort, but actually it doesn't in this case at all. If you're kind enough to pre-work the problem a little bit for your computer program, it is a lot faster to use the midpoint method, and it's a lot more accurate. Twice as accurate, in fact. Now, I was going to actually showcase how to do this problem using Excel. I think I might have even mentioned it in the video, but as I started doing it, I realized, you know what? You have Desmos. I'm not going to teach you Excel. I'm not your computer science teacher. I could easily go through and make a longer video to show you how to use Excel for this, but in the end, most students are probably just going to use Desmos. So why not just stick with that? So here we go. That's it. That's all you really need to do here. Simpson's rule is a little more complex, so we'll do that in a different video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.